In this example, we're looking at a cantilever beam with a line load which linearly increases with x. It starts out at a 0 on the left side, it gets up to a line load value there, P naught on the right. So from this we need to come up with V and M. So I'm going to do my external reactions as I do in all of these problems. Whether or not we're really going to use them or not, we can figure that out once we have it done. If I look at what's happening on this beam, we have the line load. We know it has a resultant force there, P. It has a distance of D. On the right hand side, we have a shear force, which is going to be By, and the wall is going to be putting a bending moment there of MB. I'm going to put X to the right and Y up. I'm also going to recognize here that P is equal to the area under that curve, which is 1/2 the base times the height. That looks like that. And we know that D is going to be at 2/3 of the distance over the length of the beam. So as I do summation of forces in the y direction, I simply have a minus P plus a By. So we know then that for equilibrium then that By is going to be equal to P, which is equal to 1/2 P naught times L. Summing moments about what do we want to do B, what I have here is the bending moment due to the wall, that's MB. I've got P, its moment arm is going to be L minus D, so it's L minus 2/3 L. And looks like that's it. And that's going to be a plus sign there in front. So therefore the bending moment MB is going to be minus P times L over 3. So P we said was equal to 1/2, so that's going to be 1/6 P naught L squared. 1/6 P naught L squared. So finding V is actually relatively easy here, because the line load P of x is a constant all the way across. So I have here that V of x then is going to be equal to what it is on the left hand side plus the integral from 0 to x of P of x dx. Well, there's no shear force being applied on the left hand side. When we drew the free body diagram of the original beam, we didn't show any force there because there's no external force which is acting. So this is going to be the integral from 0 to x of P of x. P of x is going to be P naught over L times x. And of course, this P naught over L is a constant, so that's going to be P naught L 1/2 of x squared. The integral of x, of course, being 1/2 x squared. The bending moment M is going to be what the bending moment is on the left side, plus the integral 0 to x of V of x dx. The left end is free as far as bending moments go. So the integral of V of x, that's going to be the integral from 0 to x of P naught over 2L x squared dx. Of course, this constant comes out on the outside, so that's going to be ending up being P naught over 6L x cubed. So that's it. Make a sketch. Well, we know the quadratic function here for V is going to be one that looks like this. Okay. The reason I know it looks like this is I know that it starts out at a 0 and the slope is a 0, because keep in mind that dV dx is equal to P. So if P is a 0 over there on the left hand side, so is dV dx. Same way there with M. This is, although v here is quadratic, m is going to look a lot like that, except it's a cubic function. And again, I draw it as I did because I know that m starts out at a 0, and I know that dm dx, which is equal to v, so it implies then that the slope of m on the left hand side is also a 0. So it starts out like that, and it increases in the positive sense as we move through. And I guess we can check our work here. Let's do some checking here. We know that v at L, according to our equation, is going to be equal to 1 half P naught over L squared. So this is going to be 1 half P naught L. And the bending moment on the right hand side is going to be equal to 1/6 P naught over P naught times L squared. And that's exactly what we got here. We said that By, our reaction at the right side, was 1 half P naught times L. By we drew as being, in fact, I need to fix up something here. Just by checking my work, did I expose an error here? Well, maybe not. By should have been down. Why is that? Oh, I see what I did. Right here, from the very start here, I made a mistake. Okay? Let me just change this. This P should have been up. Okay? Why? Because all the arrows here for P of X are up. So what that means for the force here is that P plus By, so By is a minus that. The bending moment, that is going to be a negative sign here. And so the bending moment here then will be a plus sign. Okay, now let's compare what we got from our calculations here. Yes, it was 1 half P naught L. That wasn't the issue, but it says here that the shear force should be a positive on the right face, and that's exactly what we got. We said we drew By up. We know that in fact By is down. We know down on the right face is positive. So that checks out in both sign and in magnitude. The bending moment we said here was a plus 1/6 P naught L squared. We said MB was, we drew it as being counterclockwise and right face, and that's positive. So again, we got both the right magnitude and the right sign. Always good to use as many checks as you can. Here we're checking equilibrium from drawing the FBD and writing down equilibrium with what we get from equilibrium using our nifty equilibrium relationships here of P is equal to dVx and V is equal to dm dx. So always check your work if you can.